No questions for now?
And I think the laptop is dried off.
Okay, so let's take a coffee break. We'll be back again at 11:30, and we'll talk about Fujitsu, Community Network, and IDEA.
There it is.
Let's wait for 1 more minute for folks to come back after the break. Okay. Yeah, so I guess we can get started. Hope you guys had a good break and good coffee. So we are going to start our next session. So our speaker will be Dr. Yuuichirou Ajima. He's a principal architect of Future Society and Technology Unit of Fujitsu Limited. So he is the designer of the Tofu Interconnect series, and he has received several awards, including the prestigious Medal of Honor with Purple Ribbon from the government of Japan. Today, Yuichirou will be talking about the Tofu Interconnect D of the Fugaku supercomputer and its future prospects. So let's welcome Dr. Ajima.
So today's my talk is about Tofu Interconnect D that supported the massive parallel architecture of supercomputer Fugaku. And also I talk about the future computing infrastructure of Japan. This is under discussion of our
excuse me.
community.
Excuse me. Can you please share the slides?
Oh, okay. Yes, sure. So
Just click on just share and share the entire screen. That'll be simpler. Just click on the green button.
okay.
That's yeah, and just click on share.
Maybe this one is better.
Okay.
Okay.
Yes, thank you.
It's okay.
So these are today's my topics. First, I would like to talk about the system structure of supercomputer Fugaku and its interconnect of D. Second, I will show the bandwidth hierarchy of Fugaku system and compare it with the bandwidth hierarchy of Summit. And also add the comparison slide to the frontier system. Finally, I will present the past community activity in Japan named SDHPC prior to Fugaku development and current activity named NGACI discussing the future computing infrastructure. So let's go to the first topic. Fugaku consists of about 160,000 nodes, and each node has one CPU. This is a massively parallel machine and not a fat node cluster without GPU. The network topology is 6-dimensional mesh torus with size of 24 by 23 by 24 by 2 by 3 by 2. This slide shows a packaging structure of Fugaku rack. The CPU package integrates one CPU chip and 4 HBM stacks. And CPU memory unit contains 2 CPUs. I will show pointers. This is CMU. And the next packaging structure is BOB unit in the left side. And this unit contains 8 CMU boards. And the next unit is called shelf. The shelf unit houses 3 of BLB units. And finally, rack has total 8 shelves and 4 in front of the rack and the other 4 in the back of rack. The number of CPUs per rack is 384. This slide describes the Tofu Interconnect D. The Tofu Interconnect D is integrated into the CPU chip, and the Tofu D has 6 network interfaces, and the network router has 10 ports of 56 gigabit per second link. Each port directly interconnected to other CPUs, and forming the network that has a topology of 6-dimensional mesh torus. And each network interface has a bandwidth of 6.8 gigabyte per second. This bandwidth matches the 56 gigabps link speed of off-chip connection. The Tofu Interconnect builds 6-dimensional mesh torus network. It has dimensions X, Y, Z, A, B, and C. The 3 dimensions of X, Y, and Z are scalable and variable in size, while other 3 dimensions A, B, and C have a fixed size of 2 by 3 by 2. And this slide shows the structure and topology of the CMU. There are 2 CPUs on the CMU, and 2 CPUs are connected by C-axis. There are also 2 or 3 housing for active optical cables. And each AOC has 4 lanes with 28 gigabps data rate. And 2 CPUs share each AOC, and each CPU uses 2 lanes for each AOC cable. And AOCs are connected in XY axis or XYZ axis. the average number of LC ports per CMU is 2.5. A shelf contains 24 CMUs connected in ZAB axis with a size of 4 by 2 by 3 using backplane and electrical cables. A top or bottom half of rack consists of 4 shelves connected in XY axis with a size of 2 by 2 using electrical cables. The 6-dimensional size of half rack is 2 by 2 by 4 by 2 by 3 by 2. In most cases, 2 half racks in the same rack are connected in X or Y or Z axis. The network size of Fugaku is 24 by 23 by 24 by 2 by 3 by 2. The length of Y-axis is 23. It is not an even number. And also, this is not much for half rack. Half rack has Y-axis size of 2. In fact, some half racks contains only half the node. The network size of half-mounted half racks is 2 by 1 by 4 by 2 by 3. This screenshot was taken from the Fugaku virtual tour on weekend website. From the corner of the machine room, you can see the half-mounted half racks. These 3 racks are half-mounted. And in every rack rows, the last 3 racks are half-mounted. If you are interested in, you can see these racks on the Fugaku virtual tour on Riken website. So next, I will talk about the bandwidth hierarchy of Fugaku and discuss it with a comparison to the Summit and the Frontier. And because I want to compare the bandwidth hierarchy with the GPU clusters, the Fugaku is the only Torus-based massively parallel supercomputer in 2020s. In 2010s generation, there are also Blue Q or Titans, but in this decade, Fugaku is the only machine. So we want to clarify the characteristics of the network and the difference of topology. And this is a summarized slide of bandwidth hierarchy of Fugaku system. And each CPU has memory bandwidth of 1 terabyte, oh, sorry. 1 terabyte. And 12 CPUs connected by ABC access. And this group is called Tofu. And the connection bandwidth is 27.2 gigabytes per second per node. And also, there are 16 Tofu units in the half rack. And for each CPU, there are 23.8 gigabytes per second bandwidth are used for the connection to the CPU in other Tofu, other CPUs in other Tofu units in the same half rack. The rest 17.0 gigabytes per second is actually the 2.5 links are used for the external connection between the half racks, and the dimension is used is X, Y, and Z. And each half-rack also has InfiniBand HCA for the connection to the storage system. And the generation is EDR, so 100 gigabit per second data rate. So data speed is 12.5 gigabyte per second. And there are total 828, actually, this counts the half rack as 0.5. So actually, 864 IBHCA in the Fugaku system, and the InfiniBand cables are connected to leaf switches with 36 ports, and there are 36 leaf switches, and 8 uplinks for each IB switches are connected to the spine switch that connected to the parallel 5 system. And this is the bandwidth hierarchy of Fugaku. And I will compare to the summit that's number system in 2018 that is prior to the Fugaku system. And this system consists of 4,608 nodes with 2 CPUs and 6 GPUs. This is a typical GPU cluster that each node is fat with 8 processors. And topology is 3 tiers full bisectional factory. And so this is under this hierarchy of summit system. And each CPU has 160 gigabyte per second memory bandwidth, and each GPU have 900 gigabyte per second memory bandwidth. And the total 8 processors are connected by NVLink, and each processor has 150 gigabyte per second for NVLink. And for internode communication and connection to the storage, each node has 1 InfiniBand EDR generation HCA. So each HCA is connected to 2 leaf switches by dual port. So each node has 2 ports of 12.5 gigabytes per second. And there are 2 switches in a rack. So there are total, so half of the port of leaf switches are used for uplinks. So total 36 uplinks are connected to spine switch that is connected all racks of entire summit system and also the parallel 5 system. And the summit system uses 648 port large director switch for the spine switch complex. So the comparison is start with a small scale level, and in coincidence, a single Tofu unit of Fugaku and also single node of Summit consumes about 2 kilowatts of power. So this slide compares bandwidth of Tofu unit and the Summit node that consume the same level of power consumption. Each Tofu unit has 48 HBM stacks, and each Summit node has 24 HBM stacks. This is due to the design balanced forecast of the number of HBMs of Fugaku. So the Tofu unit outperforms the Summit node in terms of HBM bandwidth and capacity for the same power budget. For internal processor connection, a single Tofu unit has total about 300 gigabyte per second bandwidth, a total of 12 CPUs. And Summit node has also have total 300 gigabyte per second. That is aggregate of NVLink between CPU and GPU. And this is the same level of bandwidth. And difference is the external connection. Each Tofu unit has about 5 gigabyte per second external connection bandwidth between Tofu units. On the other hand, the Summit node uses the hierarchical memory model, and the external connection is only 25 gigabytes per second, and the leader memory is used as a buffer. And so the Summit uses the hierarchical memory model for the programming. Comparing the two architecture, Fugaku has 48 HBMs and Summit has 24 HBMs for the same power budget. And Fugaku has succeeded in increasing the number of HBMs, but users have to use parallel programming model to only use a new number of processors. On the other hand, Summit avoids parallel programming model in use of 2K class node. So instead of using parallel programming, users are required to use accelerator programming model. And the accelerator programming model using GPU is more familiar to PC users than parallel programming. So this is the advantage of Summit system in terms of programming model. And this is additional slide that I made during this conference that compares Fugaku unit and Frontier. And Frontier's node also consumes about 2,000 watts, and the peak performance is 5 times higher than Fugaku, but the number of HBM stack are still large for Fugaku, and Frontier there is 32 HBM for in node, but Frontier used the HBM2E, the new generation of HBM stack, so the total bandwidth is nearly same. And also the difference between Summit and Frontier is external bandwidth and processor connection bandwidth. And processor connection bandwidth is 4 times higher than Fugaku because the very large bandwidth of Infinity Fabric. And also Frontier has higher external connection bandwidth compared with Summit. So okay. So, and also I compared the half rack and Summit rack. It also consumes about 4 kilowatts of power, and the peak performance is almost same. But the unit connect bandwidth of Fugaku is 10 times higher than Summit because of the topology. And Also, external connection bandwidth is higher. Fugaku is higher than Summit. For discussion, Fugaku is tightly connected to other neighbors and easy to scale out to multiple units since parallel programming is already used within a unit. And Summit nodes are connected via leaf switches. And this is the reason why the external bandwidth is small. And Summit users also begin to use parallel programming at rack scale. So this is this is a bit challenging for users to change or introduce new programming model. And it seems that Summit can increase low-cost short-range connection inside the rack in terms of hardware. But NV switch across nodes may be difficult because of the impact on the programming model. And also, oversubscribed fat tree may require locality-aware job allocation and difficult to use in system-wide operation. And this is a comparison with Frontier. The peak performance is, of course, for about 5 times higher than Fugaku. That is the relatively same power budget, about 140 kilowatt. And the difference is the unit connection bandwidth is not also unit connection bandwidth, and also bisection bandwidth in the rack is increased from Summit because of the Dragonfly topology. This is an improvement of Frontier compared to Summit, I think. So Frontier is suitable for high random communication within a half rack or Dragonfly group. So comparison of the entire system, Fugaku scales 3 times as much as Summit because of the power consumption reached about 30 megawatt. And so, but relatively the same level of system-wide bandwidth, such as bisection or I/O network. The reason there are 2 reasons, and the first reason is both systems use 4 lanes of 28 gigabps transmission technology, and the second reason is almost the same number of cables crossing the machine center line. So the bisection bandwidth is derived from the transmission technology, or more precisely, the cables, transmission technology and cables, and actually the packaging density of pluggable connectors. And the same level of I/O bandwidth is from the different reason. The reason is simple, that both systems use the similar parallel file system that Fugaku use raster and Summit use GPFS. So both parallel file system has similar characteristics, so the bandwidth is nearly the same. I also compare with the Frontier system. The Frontier system consumes about 20 megawatt in the submission for top 500. And also, Frontier's system has high bisection bandwidth due to the Dragonfly topology. But the main reason, I think, is generation of transmission technology that use 50 gigabps transmission technology, and also use the 8-lane cable and pluggable MSA is QSFP-DD. So this is reason why the improvement over the Fugaku and Summit of the frontier system. So almost out of time, but I will talk about the last topic quickly. And SDHPC was a community activity to discuss strategy to develop HP system in Japan. And discussion was strongly influenced by the exascale computing study report. And the SDHPC white paper was written in overlap with the K-computer development and released, white paper is released in 2012. The post-K feasibility study was conducted over the next 2 years, and after the feasibility study, product development started in 2014. A positive aspect of the SDHPC discussion was the accurate prediction of performance improvement trends. The performance of Fugaku follows the predicted trend, and the architecture picks the best from the multiple system models discussed in the white paper. And the ongoing community activities in Japan is called NGACI, which stands for Next Generation Advanced Computing Infrastructure. Like SDHPC, NGACI worked in parallel with Fugaku development. The objectives of the NGACI community is discuss the technology issues that need to be addressed for future high-performance computing environments and for shared computing infrastructure. The number of registered committee members is more than 100, and 4 working groups discuss future system vision and issues. And 164 pages of white paper was published at the end of 2020. The NGACI white paper predicts that top-level supercomputer performance around 2028 that will remain at a few or 10 exaflop level, and because the transistor density improvement has slowed down about 1.6x in 2 years. This prediction will be used in the feasibility study will begin this year. So I will skip this slide, and the feasibility study is scheduled to begin this year, and the feasibility study will fundamentally rethink Japan's computing infrastructure development. This study will include research on domestic and international technology trends and user needs, as well as research and development of elemental technologies. So that's it. This is my talk. Thank you for
we have time for a quick question, if there is any. If not, let's thank the speaker again. Thank you. So